Okay, so at the end of the last slide, we discussed the normal curve. We discussed that the mean is the center of your normal curve. And remember that you can change the mean, but not the standard deviation, and the curve will just move along the horizontal axis without changing the spread. So that just means if I change the position of the mean, I'm just moving this graph along the horizontal axis. It doesn't change the shape at all unless I actually change the standard deviation, which would change how far apart it is from the mean. So it'll either make it more narrow if they're closer to the mean or wider if they're further away from the mean. So the points on which the change of curvature takes place, so this point right here, that is called an inflection point. That inflection point is usually one standard deviation away from the mean. Just remember that the properties that we discussed here, they are all special to the normal distribution. They're not necessarily properties of every single solitary curve that is bell-shaped or symmetric. It's specifically to the normal distribution. Okay, so a couple of things about the normal distribution. Number one, a normal distribution is described by a normal density curve. So a normal distribution is like a specific type of normal density curve. Any particular normal distribution is completely specified by two numbers, the mean and standard deviation. So basically all that says is that the mean and the standard deviation define the curve, what it looks like, how spread apart it is. The mean of the normal distribution is the center of the normal curve. Okay, so when we have a curve that is symmetric and normal, the mean is always going to be in the center. The standard deviation is the distance from the center of the curvature to points on either side. So when we talk about standard deviation, it's always going to be positive, but keep in mind when we talk about two standard deviations away from the mean, that can mean two standard deviations above or below. So if you're discussing above or below, you specifically want to make sure that you state what you're talking about. We abbreviate the normal distribution with mean, mu, and standard deviation as n, and then you put in the mean and the standard deviation. So when you start to work with normal curves and we start to make some probability statements with them, at the top you're always going to want to put this notation right here that we're specifically talking about a normal curve with a specific mean and standard deviation. So normal distributions are good describers or good descriptions for some distributions of real data. So SAT scores are usually normally distributed, IQ tests, lengths of crickets, yields of corn, and they're helpful because they help us make predictions about these specific situations. They're also good approximations of the results of many kinds of chance outcome processes. So chance outcomes or the number of heads in many tosses of a fair coin. The reason that we need to use these normal curves is because we are going to make statistical inferences based on the distribution. So inferences just means that we are going to make some predictions based on these normal curves. All right, so just a couple things to think about. Do incomes follow normal distribution? Incomes don't necessarily follow normal distribution. They're often skewed to the right, which means they have a long right tail. Most of the people at a company will make a smaller amount of money, and then a few managers, principals, CEOs, owners of the companies are going to be the ones making more. Let's think about heights. Do they follow a normal distribution? Yes, most of the time they will, because there'll be a majority of the population of males that would be sort of in the center, and then you'll have a few males that are a little bit taller than the population and a few males that are a little bit shorter than the population. Now keep in mind though that symmetric does not necessarily mean that a curve is normal. All right, so you could have a symmetric curve that is bimodal, fold it in half, but that's not necessarily normal. So just be careful that symmetric does not necessarily mean that it's normal. All symmetric means if I fold it in half, it's the same on both sides. But the normal curve has to have its inflection points at one standard deviation away from the mean, has to be defined by the mean and the standard deviation and the properties that we talked about on the previous slide. Okay, also keep in mind you can have a curve that's uniform, so all the bars are the same height, which would actually make that symmetric, but that's still not necessarily normal. So think about, if we're looking at the ages of kids in second grade, that could, maybe they would all be 8 years old, and that would be uniform, and it would be symmetric, but not necessarily normal. Okay, so how will we be able to tell if a distribution is normal? Although there are many normal curves, they all have properties in common, which is why they're called normal curves. One is called the 68, 95, 99.7 rule, which you've probably hopefully heard about, the empirical rule in Algebra 2. So this rule is specifically called the empirical rule. Here's what it tells us. It tells us that about 68% of the distributions fall within one standard deviation of the mean. Okay, that doesn't mean it's exactly 68, but there's about 68% above and below the mean. About 95% of the data falls within two standard deviations of the mean. Okay, so within this part of the curve, about 95% of your data lies. And then we can say within 3 standard deviations away from the mean, 99.7% of the observations fall. Okay, so 68% of the data is here, 95% of your data is here, and 99.7% of your data is here. And that allows us, we could figure out what percent is one standard deviation above and below. So if 68 was here, then 34% would be above and 34% would be below. All right, so let's take a look at this one. Now, what I want to say is, in the future, we're going to be doing normal calculations. Unless it states to use the empirical rule to estimate, the only time you're going to use the empirical rule over your graphing calculator is if it specifically says to do that. So just keep that in mind. So the distribution of your Iowa test scores is approximately normal for 7th grade students in Gary, Indiana. So notice how it says, we know this notation, that means it has a mean of 6.84 and a standard deviation of 1.55. So what I'd like you to do is take a minute and try these couple of questions, sketch the normal density curve, and label the percentages using the empirical rule. So note the directions say specifically to use the empirical rule, so please do that. Okay, so notice here is our mean right in the middle. And then to get the first standard deviation, I just add 1.55, add 1.55, add 1.55, subtract 1.5, subtract 1.55, subtract 1.55. And you only need to label up to 3 standard deviations because that's where most of your data is going to lie. 99.7 specifically is going to lie between -3 and +3 standard deviations away from the mean. Okay, so what percent of scores are less than 3.74? So take a look at that curve that you have drawn and go ahead and answer that question. Okay, so if you take a look at this, 3.74 is exactly 2 standard deviations below the mean. So we want to know what is less than this part, okay? So basically what you're doing is you're taking a look and adding up all the rest of these percentages, okay? And that's why it's helpful if you go through and label, like, this is 34%, this is 34%, and then what percentage here is 13.5, this is 13.5, and then you can add the percentages below 2 standard deviations below the mean. Okay, so what percent of scores are between 5.29 and 9.94? Let's go ahead and try that. Pause it and then take a look at the answer. Okay, so that would be about 81.5% of the scores. And where does that come from? So remember that this is going to be 34%, this is going to be 34%, and this right here is going to be 13.5%. Okay, so let's try a few other questions using that same distribution. What percent of students scored an 8.39? Okay, now remember, hopefully you answered this question as none. Remember that with our normal curve, it's always a range of values. So the area under the curve is 1. Specifically, when we're talking about area, 8.39 is just one value. There's a height, but there's no width. Okay, so remember, you can never calculate a percent at a single value. So what else is important about the empirical rule? Remember that it's just an estimate. It's not the exact area under the curve, which is why in the future, you will never use the empirical rule unless it specifically states to use the empirical rule. which is exactly what that just said, okay? So the empirical rule only applies to approximately normal distributions. Keep in mind that in real life, no distributions are going to be perfectly normal, which is why we always say approximately normal, all right? And it does not apply to left-skewed or right-skewed distributions because they're not approximately normal, so that means that not 68% of the data is within 1 standard deviation, 95 within 2, and 99.7 within 3. All right, so let's just get a little bit more practice with the empirical rule. Suppose that a distribution of test scores is approximately normal and the middle 95% of the data is between 72 and 84. What are the mean and the standard deviation? Okay, what you know is using the empirical rule, we can find out that the mean is 78 and the standard deviation is 3. Well, how did I know that? Remember that 95% is within 2 standard deviations away from the mean. We know that the lower bound was 72 and the upper bound was 84. And I kind of think about this in terms of I make little things like 1, 2, 3, 4. So there's basically 4 chunks of information that you're going from 72 to 84. So if you take 84 minus 72, that gives you 12. Divide that by the 4 chunks of information, that gives you 3. So the standard deviation is 3. So if we every single time add 3, if we start at 72 and add 3, okay, that gives us 75, add 3 to 78, add 3 to 71, add 3 to 84. So can we calculate the percent of scores above 80? Well, this is a little bit trickier because this does not necessarily follow the empirical rule because I don't have an 80 right here. So we need to figure out how many standard deviations it is away from the mean. This is where you're going to use your z-scores. All normal distributions are the same if we measure in units of size, standard deviation, and mean mu as the center. All right, remember that you have your z-scores. What exactly is a z-score? It's your x value minus your mean from the normal curve divided by the standard deviation. This is going to standardize that normal curve. Okay, so if we take a look at this curve right here, a mean of 0, standard deviation of 1, that is the normal distribution where you took all of your data values and turned them into z-scores. The mean is 0 because if you take your value minus the mean, okay, if you take the value in the middle minus the mean, divided by that standard deviation, it's going to be 0 because it's a 0 distance away from the mean. Because all normal distributions are the same, when we standardize them, we can find areas under the normal curve from a single table. So the table A is a table that's in your notes. However, I would use your graphing calculator. It gives areas under the standard normal curve. The table entry for each z value is the area under the curve to the left of z. So just keep that in mind. And even with your graphing calculator, it's always the area to the left. So let's say we want to find the probability that z is less than 0.81. So you go to your table here, 0.8, and then your 10th place is 1. So right here, 0.7910. That tells us that the area to the curve to the left of 0.81 z-score is 79.10. Okay, so if you take a look right here, that area shaded is 0.7910. All right, so what I'd like you to do is take a minute and find the proportion of observations from the standard normal distribution that are between negative 1.25 and 0.81. Okay, remember that when you're doing the table, it's always finding the area to the left. So drawing a curve and shading in the area might help you do this. When you do this, if we find the area to the left of 0.81, that gives us all this area in red. And then we find the left of negative 1.25. Okay, then if we subtract those two, if we take this big area minus this small area, it will give us the area in the middle. Or just make sure that you go ahead and use your graphing calculator. It will tell you, there's directions in Blackboard on how to use your graphing calculator to find the area between two specific values. Okay. The other way to do it is just to find the whole area under the curve and then subtract the area to the right, which would be this area right here, and then subtract the area to the left, which is this portion down here, which gives you your area in the middle. Okay, so I would go to the graphing calculator notes in Blackboard and see if you can get just some practice using your graphing calculator. It's going to be much easier to do than using your table all the time. You're going to go to second distribution on your graphing calculator. Click normal CDF. That means cumulative density function. You're never going to use the PDF. You're going to type in your lower bound, your upper bound, your mean, and your standard deviation.